Okay, so actually, I didn't completely finish the feed-forward neural network, and we'll revisit a little bit of recap on feed-forward neural network. So what I showed was just a two-layer network, just to, as by example, right? But as I'm going to discuss convolutional neural networks, we'll revisit what's the difference between them, so it'll become more clear what feed-forward network really is. Okay.
We are calling it two-layer because there is an input and another is a hidden layer.
There are two W matrices, that's why we're calling it two-layer. But you can also call it one hidden layer neural network because there was one hidden layer. So when there are two W matrices, just think of it as two-layer or one hidden layer. Okay, it's nomenclature. It's fine. Okay, so uh, what is feed-forward network doing? Okay, so this whole CNN business can summarize by just one sentence. Basically, what is the motivation for a different architecture? All we're trying to do is essentially reduce the number of parameters and capture some structure in the data. Okay? Two things: reduce the number of parameters, capture some structure in the data, and you'll see that CNNs are used for images. So we'll try to capture some structure in image data. Okay, uh, and so let me discuss. Um yeah, let me discuss the what's happening in a feed forward network really. So actually, let's go back to this picture. Okay, so that so in this picture we said the W matrix. So let's say there's W1 here and W2 here, and W1 was actually um, how big was W1? Four outputs, right? Uh, the outputs of W. So when this W1 times X plus B1, this is called pre-activations, okay? Because this will be passed into that non-linearity max of 0 comma Z, and that output is called activation itself. So pre-activation, activation, the difference between them is that max of 0 comma Z operation, okay? It's like input of the max of 0 comma Z is the pre-activation, output is the activation, okay? So um, let me not fill that up. So W1 has actually 4 cross 3, right? So let's pick the first row. Okay, so there's going to be let's say A, B, C, and D. Okay, first row has 4 numbers. Actually, 3 numbers. Uh, yeah, 3 numbers. Sorry, how do I get the? Okay, that was not good. Oh, somehow I'm not getting. Okay, let's just see. Okay, so 3 numbers, right? So these and so there's let's focus on this first node. So what is that first node actually doing in terms of there's geometric representation here in terms of like this diagram. What is the computation? So this is actually supposed to represent like at least partially a computation graph. Remember we drew a computation graph last lecture when we were trying to understand backprop. We were drawing nodes which are doing some computations, right? Like even addition, we just drew a circle saying two inputs A and B, and then output is A plus B, right? So these nodes are actually supposed to represent computation. Input and output, literally no computation. Maybe some computation at the output. Input there is no computation. Okay. Hidden node. So each of these circles is actually doing some computation. So what's the computation being done by the first one is what I want to illustrate, and that's is related to the first row of the W matrix. Okay, W1 matrix. So A, B, and C, and there were some arrows here which I did not discuss at all previously. So you can see that there are 3 arrows going to the first node. Similarly, there are 3 arrows going to the second node. Similarly, 3 arrows going to the third node, and 3 arrows to the fourth node. Okay. So these 3 arrows just means that these inputs are involved in computation at this node. Okay. So both x1, x2, and x3 are needed to do some computation at the first node, and that's a neuron. Okay. And what is that computation? That computation is nothing but a times x1 plus b times x2 plus c times x3. Okay, plus the first coordinate of b11, let's say. So the b1's first coordinate. Okay, remember there was a bias as well, w1 plus b1. So let's say b1 is b11, b12, b13, and x is whatever three-dimensional vector. Okay, this b1 is this. So this is the computation happening at the first node. Okay.
Is it not also putting it through a activation function?
Yes, good point. Good point. Yeah. So this is the pre-activation, and then it is putting to the nonlinearity max of 0 comma z, and that's the output here. Okay. That's the output of this node. Yeah. Good point. Okay. So the output of this node is actually the activation, as you're pointing out. Okay. That's the computation happening at the first node. Similarly, there are 4 rows here, right? So that's you can imagine similar computation happening at the other nodes. Okay. So that's the neuron perspective of this computation. Okay. So neuron is just doing a bunch of multiplications and then adding them together, and then taking nonlinearity and spitting it out. Okay. Um, yeah. So that's actually kind of sums up feed forward neural networks. Okay. But let's think of a typical data set. Okay. So this is an example data set that you'll also work with. This is called the CIFAR 10 data set. Okay. Somewhat old. This is basically an image data set. So it's basically images of 10 classes: airplane, automobile, bird, and so on. And there are and the image sizes are 32 cross 32 cross 3. Remember we discussed this last time. What is the 3? 3 is for the 3 channels. Okay. Red, blue, and green. Okay. So the image are 32 pixels wide and 32 pixels in height. Okay. So for this data, if you really think of a feed forward neural network, how would it look like? So uh, of course we need to choose some number of hidden neurons. Let's say we do it with a one hidden layer neural network, feed forward network. We need to choose sorry we need to choose the number of hidden nodes and number of nodes in that hidden layer. Okay. And the number of weights associated with the first neuron, like just one neuron, will be 32 times 32 times 3. Right, just one neuron. In the previous slide, I just had A, B, and C. Okay, in this time I'll have 32 times 32 times 3 such weights just for the first neuron. And if I have 10 such neurons, I'll have 10 such weights, 10 times those number of weights. And if I have 100 neurons, I'll get a lot more. Okay, and if the image sizes are even bigger, then just one neuron will have. So in this case, you can see already it's about a million numbers. So about a million numbers for just one neuron in one layer. Okay, in this case, in this data, is that anybody any confusion? Okay, it's because that's the dimension of the input. I'm just thinking of the input as like a vector here.
The 3 is the RGB values?
Yeah, I mean RGB, like 3 matrices, one for red, one for blue, one for green. Yeah. So basically, all I'm trying to say is that you need a lot more, and you need many neurons, and each neuron will have so many weights, so it's like too impractical. So that's why that's one of the cons of feed-forward networks, and so we'll move to CNNs. Okay, and to move to CNNs, we'll start with again geometric picture. Okay, then we'll look at how we are reducing the number of weights. Okay, so what is the geometric picture? So the geometric picture you'll have instead of layers. So we'll still have layers, but now the layers will have some geometry. It will have dimensions. Okay, it's going to have a width and a depth. Okay. So right now, if you saw the previous slide here, a layer only had one type of property. How many nodes were there in a linear fashion? So it was just some sort of length type of property. We'll also have width and depth. Okay. and uh, and to think of that geometry, let's just transform the geometry of the feed-forward network itself into 2D, into that width and at least the width and height type of geometry. So what does it mean? So let's say I had a input image. Let's say this was actually 32 cross 3. Okay. Then remember I said I will need 32 times 32 times 3 numbers just for one neuron. So let me put my neurons, hidden layer neurons. Okay. Let's say there are 100 neurons. I'm going to arrange them as in some sort of a 10 cross 10 pattern. Okay. I just move them around. They look like 10 cross 10 pattern. But each neuron still will have that 32 cross 32 cross 3 numbers associated with that. Okay. I just instead of placing the neurons one below the other, I'm just rearranging them so that they look like a square. Okay. So that I can draw them as a square. Right. That's just a geometric thing. It's fine. And then I can also represent the score vector. It's a single one-dimensional vector, so I can represent this uh, as a vector. I mean, as a box. It doesn't matter. It's just a vector. Okay, that's not a big deal. Now, the new idea is that now we're going to have a depth. Okay, so this is essentially a feed-forward neural network. Now we're going to add depth to each of these blocks. First of all, input already had depth, right? 3 channels. But we're going to have depth in this hidden layer. So how will we do that? Okay, so height and width is still fine. So when you look at this, you should think of neurons as in those individual nodes arranged in the square pattern. So one neuron here, one neuron here, one neuron here, one neuron here. Okay, in square pattern, right? Let's say there are 100 neurons, 10 on each row, and 10 rows. Okay. Now I'm going to add a depth um, to this, which just means that now neurons are also stacked one after the other. Okay, so now neurons are not just on a plane, but there's also neuron behind it, neuron behind it, neuron behind it. Okay, that's all. So they're all neurons. They're all still connected. Each neuron still, remember, is just connected with lots of weights to the previous input, the input that is coming in. Okay. Um, okay, this is not very important. Yeah, so I mean, here I'm just showing if you have 2 layers in feed forward, then you have 2 such geometric representations. No issues. So yeah. So now I said I'm going to arrange neurons on next to each other and behind each other, and which means that remember neurons just compute one number. Each neuron computes one number, which means my output will also be like a box. It's going to be a cuboid. It's going to be a tensor. Tensor is nothing but an n-dimensional array where the dimension is like 2, 3, 4, whatever. Okay, so this is a tensor. Because I said I'm going to arrange neurons like this, the output will look like this. Okay? And in fact, in these geometric diagrams, what we're representing is the output of each hidden layer. Okay, so think of this as the input layer. This is the output of the first hidden layer. This is the output of the second hidden layer, and this is the scores. Okay? This is the output. I mean, after 2 layers, after hidden layer, whenever you get to the outputs, that's that green thing. Okay, so I just changed from 1 layer to 2 hidden layer version. That's all. Okay, so there are 2 outputs represented here. Now they are boxes. Okay. Um, Now this is a layer point of view. I'll get into the details of how we are reducing number of parameters. That was the main claim, and how we're going to use structure. So those are 2 things. So before doing that, let's still stick to the layer point of view and say, and I want to point out that there is one more layer, okay, that I want to introduce, which is pooling layer. Okay, it's a simple operation, but that can also be represented as a. It turns out that that layer just represents an element-wise operation, just like max of 0, comma z. Sorry, it's not an element-wise operation, but it's also some computation. Okay. Uh, Okay, which actually I'll go into the details of both of them. So let me not confuse you right now. So this we already saw a fully connected layer, right? Fully connected layer we just saw a couple of times. I just haven't told you exactly the convolution operation, but I'm going to now describe the convolution layer, and then we'll also look at the pooling layer. So the highlighted ones are things we'll study next. Okay. Um, but if we had those layers, let's say if we had those layers, those types of neurons and those types of computations, then we can stack these layers, which visually you'll just represent them as tensors in any way. Okay, one tensor leading to some other tensor leading to some other tensor. Whether the tensor, the new tensor maybe it's the output of a convolution layer, or the new tensor is the output of a fully connected layer. New tensor is the output of a pooling layer. It doesn't matter. Okay. You can just think of all of them as like whatever tensors they are. They could be either from any of these layers. Okay. Um, Here's so this is textual description. Let me drop it. Yeah, I mean, okay. So I'm just trying to say that you can have layers. In this case, I just stacked a con layer, a pooling layer, and a fully connected layer. Okay, just for now, just think of them as tensors. Okay, some dimension. I've not told you the details of what computation is happening in con and pooling. Fully connected, you know what's happening. Okay, and then input layer, you know, that's like, for example, in the CFR10 case, it's 32 cross 32 cross 3. Con layer, okay, the neurons are just like feed forward neurons. Okay, the neurons are just like feed forward neurons. They sum the products of the inputs with the weights and add some bias. Okay, we saw that computation, and um, they may output uh, yeah, the output of the con layer can surprisingly have a different number of different dimension of that box compared to the input tensor. Okay, and I'm going to describe the detail pretty soon. Okay, that's the only difference. Otherwise, and just like, you know, in feed forward layer as well, the number of hidden neurons you choose determine how big the activation vector was, right? Or irrespective of how big the input was, right? So output can change based on how you specify the layer. So con layer also can change it. And pool layer is actually a pretty simple layer. So let me explain it here itself. What it does is it downsamples a tensor. Okay, so let's say I had a matrix which was 4 cross 4, which means that I had 16 numbers. A pool layer essentially is like trying to say, oh, I have this huge matrix, it has 16 numbers, I can't really tackle all of them. Let me do a 2 cross 2 matrix. Okay, I'll have 4 numbers. So from 16 numbers, I need to go to 4 numbers. That's a downsampling operation. Okay, it's like reducing, like somehow forgetting some numbers, right? From so many numbers to only 4 numbers. So that's what pooling does. Okay, and we'll see how. And so typically, what pooling will do is only work in terms of like 2 of the dimensions, like the spatial dimension, height and width. So you will see some reduction in numbers. Okay, if it was a 32 cross 32 matrix, like each slice is a matrix, right? That will change to 16 cross 16 or 16 cross 16 to 8 cross 8 or something like that. Okay, that's typical operation. But we'll get into the detail. And fully connected is just what we know already. Um, yeah, so that's fine. Okay, so let's focus on the con layer. Um, so so in the pictures, in the diagrams, we were only looking at the outputs of the layers. Okay, those tensors were the outputs of the layers. Now we look at what operations led to such an output. You know, tensor of a different size. Okay, so the operations are gonna will have parameters, just like the fully connected layer had parameters, the weights, the W1 matrix, W2 matrix. These con layer will also have parameters. Okay, but I'll not directly call them weights. I mean, you can call them weights, but there's some more adjectives I will add. Okay, those parameters, I'm going to call them a set of filters. Okay, a collection of filters. Okay, note the word set. Set just means I have more than, I have like 3 filters or 10 filters. So whatever the 3 or 10 is going to be the output depth of the tensor. Okay, if I have 10 filters, I'll have output depth 10. If I have 12 filters, I'll have output depth 12. Okay, so let's think of the image 32 cross 32 cross 3. I have let's say I have 12 filters. Then my output, I haven't told you some other properties, but output depth will be 12. Okay, right? So the set is just saying how many filters I'm going to apply. So filters are nothing but collections of weights. So you can call them weights as well, but filters is like a little bit more nuanced. And what is a filter? A filter is just a linear operation. Okay, so a filter is just linear operation, and output a single number. Okay, so it's like whatever is the input somehow compressed to a single number, just like a neuron, right? And output that number. That's what a filter does. Okay, and the parameters of the filter are just are weights, and so we learn it during training, just like in feed-forward networks we would learn it during training. Okay, so so here is an example of a filter. So here is an example of filter which will have filter is just a collection of weights. Filter itself is a collection of weights. So one example is a 3 cross 3 cross 3 filter. Okay, so why are the 3 numbers? Because the input dimension sorry why are the 3 numbers? Because the input has three dimensions. Okay, that's why there are 3 numbers, and of course the 3 numbers correspond to some height, width, and depth. Okay, the filter just means that, so this just represents basically a tensor. Okay, so 3 cross 3 cross 3. Okay, Okay, 27 numbers arranged in a cuboid format. The first two represent, I guess, pixel width and height. Okay, the last one represents filter depth, and filter depth is going to be the same as the input tensor depth. Okay, that's one property of this collection of weights. I mean, I'm going to arrange these weights such that the depth of the filter is the same as the input depth. Okay, and next, what we're going to do is we're going to convolve the filter. Okay, convolve just means element-wise multiplication for us. It's essentially what it is across the width and height of the input volume. Okay, so let me show it by diagram, which actually I should go here. Uh, what was it called? Image kernels. Uh, okay, actually, this is better. So here is a 3x3 filter. Okay, just ignore all the words here. Doesn't matter. So this is a 3x3 filter with no depth. Okay, so depth is just one. Okay, let's think of it's 3x3x1. I told you the depth has to be the same as the input depth. It turns out, I mean, here we're working with grayscale image, so there is no RBG, so there is no depth here. It's just one. Okay, so what is the filter is doing? A filter is just three. This 3x3 numbers in this case, right? 9 numbers. So it's just multiplying the entries of in this image. So this is an image, grayscale image. So each entry is a value between 0 to 255. It just happens. I mean, some scaling. Okay. These are the colors. Okay. Darker color means lower number. White means 255. Basically, in this image, and it's just multiplying element wise with the image entries. Okay. So element wise multiplication. It's just a matrix element wise multiplication. That's what's happening. Okay. And then you add them together. Add all these numbers together. Whatever number appears, that's the number here. Right? Is the single operation clear? And then I'm gonna just slide the filter to the next. Just slide the filter. I mean, visually we are sliding it, but ultimately just moving one step forward and producing one more number. Moving one more step forward to the right, producing one more number. That's what I mean by slide and convolve with the input. Okay. So on the spatial dimension, width and height dimension, we are just sliding the filter to the right and to the bottom, and we're getting this final image. So that's what happened here. Okay. So this image with that filter I showed you, whose entries were 0, minus 1, 0, something, something. Okay. When you multiply it, you'll get something like this. Okay. Now we ask, oh, what is the dimension of this thing? Okay. Of course, my filter was 3x3 in terms of spatial width. That influenced how big this image would have looked like. This output would look like. It's not. I mean, it's an image here, but some output, okay, would look like. So the choice of 3x3 gives you an output which is, I guess, one dimension less on each coordinate. Okay. So you can see that over here. So if I start from, they're computing. Okay. So yeah, they're starting from here, which means that as if they've added some no entries or whatever, question mark entries, and so they have some black there. But the dimensionality of the output just depends on the size of the filter and whether you're adding what is called padding. Okay, so I'm going to discuss padding in a minute. Is the filter sliding operation clear? At least filter is nothing but a collection of weights. I'm just using the same weights to compute in different patches of the input in this case, and then computing a single number and producing it on the outside. Okay, output. Like in this case, if this was the input with numbers in the orange, and if my filter numbers were the red numbers multiplied together, one number. Okay, and you can get the remaining numbers. So you can see that if I had a 3x3 filter on image, or sorry, not image, but whatever, of an input which is 5x5, I would get a 3x3 output. Okay. You can just see the dimensions have to, it's just, But what if I had put padding of zeros around it? I would have gotten a 5 cross 5 image. Okay, so 5 cross 5 output. That's just an intuition. Um, so filter depth, three things to notice. First is filters are small on width and height. 3 cross 3 filter is like just 9 numbers. Filter depth is the same as input depth, which I mean that right now in the examples that I showed you, the filter depth was just 1. So if the input has depth 3, then my filter would just not be 3 cross 3 numbers. It will be 3 cross 3 numbers. So why the third 3? Because the input depth is 3. If the input depth is 5, then 3 cross 3 cross 5. Okay. So that would be my filter, collection of numbers. And then what would I do? The operation would still be the same. I'll take that block, element-wise multiply with the input block. It will work out, right? Because the spatial dimension is fine. And depth also I can do element-wise multiplication, right? Because literally same depth. And then sum all the numbers. I'll get one number, and that's the output. Okay, at that region. Then I slide to the next, collection of in the spatial dimension. Again, I can multiply, add, and then produce one number. Okay, that's the what the filter is doing. And as we slide, we are producing one number for a single number for a filter, right? As we slide on the spatial dimension, we're getting one number, right? So ultimately, we're getting a matrix, right? One number per region, and I'm sliding forward, backward, down. So I'll get a bunch of numbers, and it will be arranged exactly like a matrix. Okay, and we saw that in the previous slide, right? This is a matrix. Even if there was depth, ultimately you will get a matrix. Okay, so that's called a 2D activation map. Just nomenclature. Okay, and yeah, and don't worry so much about this point. It's all it's saying is that these numbers in the filters have to be learned. Okay, just like gradient descent, but that comes later. So before we look at how the entries of filters look like and so on, because we saw entries of the filter in that web page, right? Let's look at how three things. How are they connected? Okay, I mean, how are they related to a neuron concept? Because feed-forward networks, there is a concept. I mean, all the first row of the weight matrix was essentially the numbers corresponding to neuron. So what's the equivalence here? And if there is a neuron idea, then how are they connected? How are they arranged? And what is this parameter reduction that I mentioned at the beginning? Okay, so actually, let's directly look at a picture. So how are the neurons connected? So we just discussed filter, right? So there could be many filters. Okay, so I just described the operation of one filter producing one 2D activation now. Let's say I have 10 such filters, 10 such 10 small tensor blocks. Then I can have 10 such 10 such matrices output, right? So all those matrices, if I can ensure that the filters are not are similarly shaped, then all those matrices may have similar shape, and I can stack them together. That's why I'll get a tensor. Okay, so that's the tensor that I'm representing here in blue. Okay, and now I'm gonna tie this back to the idea of arranging neurons. Okay, remember I said arrange neurons in a convolutional network like a tensor. So each number here is like the output of a neuron, because I said if you arrange neurons like that, that's why your output tensor is like that shape, right? So each number is the output of a neuron. So you can as well imagine that there's neuron here, right? And the neurons are stacked one next to the other. So what is this depth? Like why are there 5 neurons stacked in this case? Is because maybe I had 5 filters. Okay, so the number of neurons, the output depth is the number of filters. Okay, so the number of filters determine the output depth, and each neuron, it's as if it's only connected to a part of the input region. So let's focus only on this neuron, okay? Which means that this neuron corresponded to some filter only, right? Like there was one filter which corresponded to this neuron. Now that filter was, let's say, 3 cross 3 cross 3. Okay, that means that the location of the neuron influences like which of the input 3 cross 3 cross 3 block that filters 3 cross 3 got multiplied element wise and added up together, and that number got produced. Okay, so it's as if this neuron's output is only being computed because of this region of the input. Okay, if it's actually the input image, then this is the only region of the input image that was seen by this neuron to compute something. Okay, and now Yeah, I mean some parameter computation. And if you look at this, all these 5 neurons are looking at the same region, okay, but they're using different filter weights, okay, because they're in the depth situation. But the neurons on the same activation map, a slice of this tensor, they're all using the same weights, okay, because they're all using the same filter, and same filter means same weights. Okay, so each whole slice is using the same number of weights. Okay, instead of each neuron using different weights, which was the case in the feed-forward network. And each neuron is only looking at a small part of the input, rather than being connected to the whole input. Okay, so those two aspects reduce the number of parameters for convolutional layer. Is that clear? Okay, so there is some additional, I guess, nomenclature. So layer depth is the number of filters. Okay, I mean, if I have 5 filters in the previous picture, there were 5 filters, so depth was 5. And stride is how much is the filter moving in the spatial dimension. So I could have just moved 1 pixels to the one, not pixels, but let's say 1 row to the right, or 2 rows, jump to 2 rows, jump to 4 rows. That's all choice, right? So that's called a stride. And there's also this notion of zero padding, because we saw, where is this? Yeah, in this example, for example, there is no zero padding. Okay, in this example, this is the input, and so my output is 3 cross 3. If I put a bunch of zeros next to it and make it a 7 cross 7 matrix, it's a 5 cross 5. If I put a bunch of zeros all around it, it's going to become a 7 cross 7 matrix. 2 rows to the left and right, 2 rows to the, sorry, 2 columns to the left and right, 2 columns to the 2 rows to the top and bottom. So we can 7 cross 7. Then if you do a 3 cross 6, operation with one stride of 1, okay, then you'll get a 5 cross 5 matrix. Okay, it'll be the same as the original input size before the zero padding. Okay, so that's what zero padding just means. Zero padding is just trying to adjust. Oh, if you put zero padding, you will change the dimensionality of the output tensor in terms of the spatial dimension. Okay, that's all. And the number of filters determines the depth of the output tensor. Okay, so yeah, I mean, I should have gone to this slide. Stride is 1 and 0 padding is 0. Yeah, and so as I said, each slice or 2D activation map is using the same filters, and um, that's actually using the structure of images. Okay, some structure of the images. Basically, for example, if you want to detect like an edge or a pattern in the image, then the same filter can search over the region. It's like translation invariance. You're trying to say, oh, if there's a curve for, let's say, the wheel of a car, then I can find the curve somewhere in that image. Okay, maybe a filter is going to specialize. I mean, of course, the weights have to be learned through some training, supervised learning procedure, but maybe this filter will specialize to detect that curve. Okay, that's essentially what's happening. Okay. Uh, yeah, as I said, all neurons in the same depth slice use the same weights and bias parameters, and that reduces the number of parameters. For example, if the number of filters is m, and if filter size is 3 cross 3 cross 3 and plus 1 bias term, so you can just add one number to every neuron, right? Just like in the feed forward case, you were adding one bias, one additional constant in addition to a times x1 plus b times x2 plus c times x3. So these are the number of parameters. Okay. Contrast that with a full, what is it, a fully connected layer. There's quite a bit of reduction. Okay, because you get to choose the number of filters, and then each filter is like really small number of numbers. Okay, because it's only looking at a small range, and they're getting reused throughout that particular activation. That particular slice. Um, so here are some, I mean, this is not so much of an intuition. These are just examples of how, I mean, in that network from 2012, there was some network, okay, in 2012, the convolutional network. It's called AlexNet now. And that network's initial filters, they were like 11 cross 11 cross 3. Okay, it's not 3 cross 3 cross 3, but 11 cross 11 cross 3. And the team chose 96 as the number of depth. Okay, so the output tensor was 96 times some spatial dimension determined by whether they added zero padding or not. Okay, but here I'm just showing the uh, filters, and filters, since they have depth 3, you can actually visualize them as images. Okay. If they have depth 4, it's not clear how to visualize them as images. Okay. So I mean, here they're trying to show that okay, each filter is probably trying to detect an edge. Like basically, what is filter doing, right? It's just multiplying the input image, and if the input image has a similar pattern, if you do element-wise multiplication, typically that output will be high. Okay, it's like a detector of some pattern. That's what's happening. Uh, Let me not go into that example. And actually, you can look at that website, and there's a nice animation for how this multiplication is happening. If you really want to reinforce your understanding of what the convolution layer is doing, let's go to the pooling layer. It's vastly more simpler than con. Okay, that was the toughest part of this lecture, I guess, in terms of imagination. The pool layer is just there to reduce the number of numbers that I'm going to process. So if I had a tensor, which is like 10 cross 10 cross 50, okay, some 50 depth and 10 cross 10 cross 10 cross 10 size. There are too many numbers, like 10 times 10 times 50 is a bunch of numbers. Now I want to just change that to keep the 50 the same, but instead of 10 cross 10, maybe I can make it 5 cross 5. That's the motivation. Pooling. Just reduce now. Somehow downsample, coarsen my data. Okay. Um, so this is how we're going to do it. This is an example. So if I had to put an interval student 4 cross some depth, okay, maybe at some part of like this. Let's say this is the output of some con layer in your layered architecture. Pooling all is just at least typically what we refer to pooling. It will not change the depth. Okay, it's the same. But on each slice, it will just somehow make it lower resolution. Okay, that's what it is. And what is in each slice? It's a bunch of numbers, right? It's just a matrix. Each slice is a matrix. So how would you reduce the dimensionality? Here is an example. Let's say this is a slice with 4 cross 4 numbers, and I want to change it to cross 2. What will I do? Maybe I'll take the maximum of those 4 numbers. That's what is in this example. That's what I'm doing. Okay. So it's coarsen the data. I lost the fact that there was 1 and 5 next to 6, and I just took 6. Okay. So I'm picking 4 numbers out of this 16 numbers. Okay, that's what pooling is doing. This is called max pooling. Okay. You can also do other types of pooling, like just take the average of the numbers, take the minimum of the number, whatever you want. But max pooling tends to be what gets used. Okay. Yeah, fully connected layer we already saw, and I could show this animation, but I think we are already exhausted. Many of you, I see. So open this up, I guess, and see for yourself. So that's for the lecture part. So we saw free forward network. So just think of what's happening is just a bunch of multiplication operations and additions, and then some nonlinearity and passing forward. That's what, if you really think of like a really small scale example and draw the computation graph, that's what's happening. Okay. And so and once you draw the computation graph, you don't even have to think of neural networks anymore. You can just think of backdrop. Oh, okay, something is getting computed at the end. I want to find this gradient with respect to some input. You can find it. Okay. That's just mechanical, and that's what the softwares do. Okay, backdrop. Anyway, today we saw feed forward CNNs, and I didn't spend too much time on like why CNN. Is that this notion of filters and so on came from signal processing, and it's basically trying to exploit some aspect of images. Images have, for example, spatial invariance, right? Whether the cat is at the top right, or the bottom left, you should ideally detect where the cat is. So these filters, which are convolving or sliding through the input, at least at the beginning layer, they are trying to detect like spatial invariance, and even the intermediate layers you can still interpret it that way. Okay. And they are really capturing the locality of information. So it's not like you'll detect a cat by finding something so far, even at the beginning itself. So eventually, after a few layers, then a column layer at the end may get to see the full image in an indirect way, but the first filter will probably not see the full image. Probably see 3 cross 3 part of that image. Okay. So that's some locality and spatial invariance being captured, and that's also the other idea is that there has to be hierarchy of features. First, you detect edges, maybe there are curved edges, and then maybe later on you detect, oh, there's a wheel, and maybe you detect 2 wheels, and later on you detect a higher level pattern of like a wheels, geometrically like this, and then you detect a car. Okay, so that's hierarchy of features kind of idea, intuition. These are all intuitions for like justifying the architecture. But ultimately, the architecture is what you saw at the beginning of the lecture. It's just a composition of functions, like w1 times w1x plus the b1, the holding max operated, and then another bunch of matrices. That's what it is, mathematically. But these are all geometric intuition for that. Okay, so that's for the um, yeah. So that's for the lecture part. I think I'll probably revisit PyTorch basics next lecture, and you can actually try this. You can try. So this one we just saw. I did not execute it in real time, but you saw it. Right? Feedforward network was able to capture the pattern, maybe it overfit, as you were saying. So we saw this notebook, but these two we did not see. This one is actually a GitHub repo where you can click on run on Colab. So if you're interested, you should also try Google Colab. By the way, how many of you have not heard of Google Colab? Okay, just you when you click on this repository, you click. There's a nice README file which has links to directly open that notebook in a Google Colab. So it's essentially this is what this is. Actually, this is the repo, and I clicked on this one, open in Colab. If you're already signed into Google, it will literally do that. And this is the same uh, Python notebook. Okay, so you can look up. So this notebook is talking about PyTorch basics. So we'll use PyTorch most likely in this course. So PyTorch is another package like NumPy, and here in fact they're showing that how if you do np.random.random, you'll get a random matrix, and if you do toss.random, you'll get a random matrix as well. But as a tensor data structure, which is more useful for like pushing it to GPU and back. Okay, so try to go through this tutorial. If not, we'll actually revisit some important parts of this tutorial next lecture. Okay. Okay, that's it for today. If you have questions, come to the front.